Sir,
Yes.
you will start, sir.
Hello, everyone. Welcome to the course on earthquake seismology. This is your instructor, Mohit Agrawal, and we are going to have our live lecture 2. And since we did not receive queries, so I will continue with the explanation of the assignment and the important questions that are supposed to be discussed. And in the last lecture, we have covered 4 assignments. So today we are going to start with assignment number 5. There we have a question number 2. In the question number 2, that says a zero offset reflection event at 1 second has a normal move out, that is in short known as NMO, of 0.005 second at 200-meter offset. What is the approximate stacking velocity? So we are supposed to find out the stacking velocity, and if you could recall the lectures in the module 5, I discussed about stacking velocity. So I encourage you all to basically look at the lecture to have more insight into it. But just for the sake of solving this question and finding the velocity, that is stacking velocity, then what we can do in this question, we know that the normal move out that we are talking about is basically is given by a formula, that is T of x minus T naught, that is equal to x. X is your offset distance, divided by v bar square, that is your stacking velocity square, that here we are supposed to find out, plus T naught square to the power 1 by 2 minus T naught. So Tx is the two-way travel time for x distance offset, and T naught is for the zero offset. And here in this question, Tx minus T naught is basically given. That is, you can see from the question that is given, that is your 0.005 second. So we can keep it here, 0.005 and second. And in the question, the value of T naught is also given. So that is 1 second, or you can say 1.000 seconds. And the offset distance is given, that is 200 meter. So when we keep all these values, so Tx minus T naught and the T naught values, and x is 200, then you can easily find out the value of v bar square, or you can say the stacking velocity. So while by putting these values and solving, so it will give you basically the v bar. So that is equal to 2000 meter per second, or you can say 2 kilometer per second. So if you look at our options, then option number B should be correct. That is 2 kilometer per second. So likewise, if we go ahead and solve another question that is also seems like a little a typical question. So you can solve this question like the question says that a single-ended refraction profile designed to determine the depth of an underlying horizontal refractor reveals a top layer velocity of 3 km per second and the refractor velocity of 5 km per second. So basically, in this question, if you look at, then the top layer velocity is given, that is 3 kilometer per second, and the velocity of half space is 5.0 kilometer per second. So, and the thickness of the layer that is given is equal to 500 meter, or you may say 0.5 kilometer. So, you know what is the crossover distance? So, crossover distance is the minimum distance after which the head wave start to appear earlier than the direct wave. So basically, let's suppose you have a source here and you have a receiver here. So what will happen? You will have a direct wave that will go from source to receiver, and you will also be having a reflected wave that will go and reflect off from the interface and then recorded at the receiver. And there will be a third wave like this that will be traveling in the layer, and then it will travel along the interface if it is having a angle that is equal to the critical angle, and then it will go back to the receiver. So when, so you know this direct wave, this is the direct wave which is traveling with the velocity of the top layer, and the head wave, this is the head wave here, which is traveling with the velocity of the medium beneath. So after a certain distance, this head wave will be coming earlier than the direct wave, and the formula of crossover distance says that xd, this is your crossover distance xt, that is 2h naught in bracket v1, that is your half space velocity, plus v naught, this is your medium layer velocity, divided by v1 minus v naught to the power 1 by 2. So you can see that V1 is given. So V1 is basically your 5 kilometer per second, and V naught is also given, that is your 3 kilometer per second, and your crossover distance is also given, that is your XT 500 meters. You can convert it into kilometers also. And then if you incorporate all of these into this formula, then you can readily find out the value of H naught, that is your thickness. So this is what it is asked, what is the refractor depth? So depth of the refractor. I am sorry, the thickness was not given. I am sorry. So it was 500 meter was the crossover distance. So, XT, if you are going to put in 500 meter or maybe uh, divided by 1000, so it will be in kilometer. 2h naught, h naught is required to be find out. So 5 plus 3 divided by 5 minus 3. So when you will solve this, then what you will find out? You will find out the refractor depth of the refractor, that will be equal to 125 meter. So when you look at your options here, you will see option number C is correct. Now let's move on to the next question in the same assignment, assignment number 5. So question number 7 we are going to discuss in assignment 5. So this question says the horizontal and the vertical slownesses of a layer are 0.15 and 0.20 units. What is the magnitude of the slowness? So you know that horizontal and vertical slownesses are the vector quantities. So you can find out the magnitude of slowness just by taking the under root of horizontal slowness square plus under root of vertical slowness square, and you should be able to find out. So we can say that the magnitude of the slowness vector is can be written as under root of p square plus eta square. So P is your horizontal slowness and eta is your vertical slowness. So we can write this is your horizontal slowness, and this is your vertical slowness. And values of both are given. So horizontal slowness is basically 0.15 units, and you can say units, and this is your 0.20 units. So the magnitude you will find out under root 0.15 square plus 0.20 square, and when you solve it you will get on calculating 0.25 units. So if you look at your options, then based on your option number C is correct. That is 0.25 units. Now let's move ahead and look at the questions in assignment number 6. So today we will discuss up to assignment number 8. So in this assignment, question number 2 we are going to discuss about, and this question says that for a flat earth consideration, the arrival time of a seismic phase at two nearby stations is 0.15 seconds and 0.45 seconds. So, given the apparent velocity along the surface be 4.5 kilometer per second, the approximate interstation distance. So we are required to find out the interstation distance. So you can see the arrival times are given at two nearby stations for the seismic phase. So there is a seismic phase uh, for flat earth we are required to consider. So when the seismic wave is traveling, then at one station, so let's suppose this is your station 1 and this is your station 2. So seismic wave is traveling. So a seismic wave is coming like this, maybe. So at first station, it is reaching at around 0.15 second. At another station, it is reaching at around 0.45 seconds. Okay, and apparent velocity along the surface is also provided. So apparent velocity, you can write apparent velocity along the surface that we can write as dx by dt. That means distance divided by travel time difference. Okay, so we can say here dt is the arrival time, is the arrival time difference between the stations with interstation spacing dx. Okay, so if you look at this formula, apparent velocity along the surface. So apparent velocity, if you look at the question, it is given that is 4.5 kilometer per second. So we will use that. So using this formula, we will write 4.5 will be equal to dx divided by arrival time difference. So dt is how much? 0.45 minus 0.15. Okay, because at one station it is coming at 0.15 second and at another station it is coming at 0.45 second. So when we solve this equation, then dx you will find out to be equal to 1.35 kilometers. So this is the interstation distance between both of the stations. So what you will see here, they are asking for the answer up to 2 decimal places. Look at here. So this is answer up to 2 places after decimal, and we are required to fill this blank. So our answer that came out to be 1.35 kilometer. So this is your 1.35 kilometer. Okay. Now let's move on to the next question of the assignment number 6. And this question is about the ray parameter. And the question says that a ray were leaving the source at an angle of 150, 150 degrees, bottoms the depth of r is equal to 5,000 kilometer at a velocity of 8 kilometer per second. The ray parameter at the bottoming depth is. So basically what it is saying is that the ray is leaving the source. So ray is leaving the source at some angle that may be, I think this should be 15 degree. So it is 15 degree, and bottoms the depth of r is equal to 5,000 kilometers. So when the ray, let's suppose this is your surface, okay, and from the surface ray is going like this, okay, and if you consider this as the center of the earth, then the bottoming depth, let's suppose this is your bottoming depth from where the ray has moved into upward direction towards the surface. This is the deepest point that the ray is traveling from the surface. So if you look at this point, then from the from the center of the earth, this distance is 5,000 kilometer. So basically you can say that this is basically your r. So you know that the ray parameter, what is ray parameter? Ray parameter, from the Snell's law, we know that ray parameter along the entire path of the ray remains constant, and it is represented by P, and that is equal to R sine I by V. This is for spherical earth. Okay, so ray parameter P is equal to R sine I by B, and at the bottoming depth, if you look at, the angle is 90 degree, right? So this I at the bottoming depth will be 90 degree, and this R will be 5,000 kilometer. So what we are going to do, we are just keep trying to find out the value of P at the bottoming depth. So P is equal to 5,000 into sine I, that is 90 degree, divided by V, that is your 8 kilometer, that is given in the question. So this is your 8. So when you solve this, then what you will get, this P will come out to be 625 units. Okay. So now when we are looking at our options, then you can say that option number C is correct, which is saying 625 units. Now let's move further. There is a question number 10 in the assignment number 6. It says SCS is more prominent on the seismogram than PCP because the options are given. PCP attenuates at the surface. SCS constructively interfere near the surface. The liquid core does not transmit shear waves. And then there is an option D. All options are correct. So first we need to understand what is SCS. Okay, so let's suppose this is your inner core, this is your outer core, and this is your mantle. Okay, and maybe there is crust also, but that is very thin in comparison to the other layers of the earth. So let's suppose there is an earthquake in the mantle. So there is a earthquake, this one. So from these earthquakes, the shear waves are propagating, or you can say emanating. So when these shear waves are going down and then gets reflected from the outer core and then recorded at a receiver on the surface, then the path will be shear wave, then getting reflected from the outer core. That is why we have this term C, and then coming back as shear wave to the receiver. So this entire path nomenclature is SCS. Likewise, you can talk about PCP wave. If suppose there is a wave that is traveling from the same source maybe and going down as P wave, getting reflected from the core, that's why C term will come up and then gets recorded at the receiver. Okay, so this is your PCP. Now the question says SCS is more prominent on the seismogram than PCP, because yes, this is true, because what happens, the outer core that we say, so this is your outer core, this is your outer core, this is your inner core, and this is your mantle. And we know the outer core is liquid in nature, or if a is fluidic in nature. So we know the shear waves cannot travel through the medium that is liquid. Okay, because it does not have any shear modulus. So in that sense, what will happen? The shear wave that are coming from the source to the outer core, the zero amount of energy, or you can say the amount of energy that will be refracted into the outer core will be almost negligible. So entire energy of the shear wave after it impinges at the outer core will be reflected back and received at the receiver. While in case of PCP, the P wave will go down like this, P wave is going down like this, and then at the outer core and the mantle boundary, because P can travel into the liquid medium or the outer core, then some of its energy will be transmitted into the outer core, and some part of the energy will be reflected and will be received at the receiver. So that is why the SCS phase will be having higher amplitude, or maybe much clearly visible onto the seismogram than the PCP waves. So when you look at your options, then PCP attenuates at the surface. This option is not correct. SCS constructively interfere near the surface. This option is also not the region for the SCS waves to be prominent on the seismogram. The option C, the liquid core does not transmit shear wave. So this option seems correct. So option number C should be correct. Now we are moving upon to assignment number 7, and we will be discussing in this assignment two questions. We will be discussing around three questions in this assignment. Assignment number 7, question number 2 that we will be discussing about. So for P waves in olivine nephelinite crystal at pressure 0.1 megapascal, alpha max, that is the maximum P wave velocity, is given, that is your 6.81 kilometer per second, and the minimum P wave velocity is also given, that is 6.45 kilometer per second. And mean P wave velocity in the olivine nephelinite crystal at zero point 0.1 megapascal is also given, while at pressure 400 megapascal, the same values for P wave are given. The approximate ratio of the magnitude of anisotropy at zero point 0.1 megapascal to 400 megapascal is. So we are required to find out the ratio of magnitude of anisotropy. So magnitude of anisotropy is given by a small k, that is equal to V max, maximum velocity in the crystal, minus minimum velocity in the crystal, divided by the mean velocity of the phase or the wave in the crystal. Okay, so first we will talk about at 400 megapascal, or sorry, at not 400, at 0.1 megapascal, the values are given. So like LV max is given. So we are going to find out K at zero point 0.1 megapascal. So that will be equal to the V max, that is your 6.81, minus V minimum, that is 6.45, divided by V mean, that is 6.71. So when you will calculate it, it will come out to be 0.054. Likewise, at 400 megapascal, when you will calculate the magnitude of anisotropy at 400 megapascal, then it will come out to be 6.95 minus minimum velocity, that is 6.78, divided by mean velocity, that is your 6.88, and when you will calculate it, it will come out to be 0.025. And now we can easily calculate the ratio, that is k 0.1 divided by k 400, and that will be equal to 0.054 divided by 0.025, and when we will solve it, it will be 2.16. So the ratio is 2.16. So when you will look at the options here, then option number B is correct. Now let's look at the question number 6 of assignment 7. Question number 6 says, assume a P wave is traveling in the lossless medium with a velocity of 8 km per second. The ratio of amplitude at a distance of 16 meter to the amplitude at the distance of 8 meter from the source is. So we know one thing, the body wave attenuation, the geometrical factor, or the body wave attenuation with respect to distance is proportional to 1 by distance, or 1 by r. So amplitude, you can say the amplitude of the body wave decreases by a factor of 1 by r. Okay, hence you can find out the amplitude ratio, that means at 16 meters. So amplitude at 16 meter divided by amplitude at 8 meter distance, and that will be inversely proportional to the distance. So it will be equal to 8 divided by 16, and that will come out to be 1 by 2 or 0.5. Okay, so option number B is correct. Now let's look at the another question in the same assignment, which says, in a harmonic motion, the amplitude of a wave of 4 seconds of 50 nanometer, and the difference in the amplitude in two consecutive maxima is 5 nanometer. So this is the condition given. Q is greater than 1. That is attenuation, or the quality factor is given, that is very larger than 1. The value of Q to the nearest integer is, so we know that if you could recall my lecture, for Q greater than 1, we basically know that this Q is given by a formula, that is pi divided by ln A1 by A2. Okay, so what is given? A1 is given, that is A1 is equal to 50 nanometer, and A1 minus A2 is also given, that is 5 nanometer. Okay, and when we put all these things into the formula, that is Q, then value of Q will be pi divided by ln in bracket 50 by 45. Because if you put A1 into this formula, into this A1 minus A2, then A2 will be equal to 45. So when you solve it, it will come out to be 29.8 to be accurate, and approximately it will be equal to 30. So in the blank, you can fill 30. Now let's move on to the assignment number 8, and I found there is only one question that requires discussion. The assignment 8, question number 4, the bulk modulus and density of quartz are 37 gigapascal and 2.65 gram per centimeter cube respectively. The P wave travels at a speed of 7 kilometers per second. The velocity of S wave we are required to find out in kilometer per second up to 2 places after decimal. So this is a very simple question, since we know the relationship, that is alpha square minus 4 by 3 beta square, that is equal to k by rho. So you know alpha is p wave velocity, beta is s wave velocity, k is modulus of this is k that is given for bulk modulus, and this is your density. So when we incorporate, so what is given? So what is given? K is given, that is your bulk modulus, that is 37 gigapascal, and when we converted it to Pascal, then we are required to multiply 10 to the power 9, that is your 37 into 10 to the power 9 Pascal, and rho is equal to 2.65 gram per cc, that is equal to 2650 kilogram per meter cube, and alpha is also given, that is 7 kilometer per second. So when we put all these values, so on putting these values, these values and solving for beta, so what we will get? 7,000 squares, because our formula that we just saw, alpha square is equal to minus 4 by 3 beta square is equal to k by rho. So 7,000 square minus 4 by 3 beta square, that is equal to 37 into 10 to the power 9 divided by 2650. So this is your density that we just saw in kilogram per meter cube. So after you solve this, then you will get beta, that is equal to 5126.23 meter per second, and that is equal to approximately 5.13 kilometer per second. So this is your beta. So in the question, this is what they are asking about. What is the value of shear wave velocity? So that is equal to 5.13 kilometer per second. So in today's live lecture 2, we are going to finish here. So this is assignment number 8 that we discussed today. In the next live lecture, apart from queries, we will be discussing about rest of the assignments. So we'll be in touch, and welcome again. Thank you. Bye-bye.